Hello everyone, welcome to this new problem where we are going to go through count the number of computer unlocking permutation. So what is happening here is that you have I won't go through all of this. I'll just summarize what we have to do here. So the situation is that we have an array of integer where each of the integer actually represent the complexity of a log. And then the scenario is that the first element of the array is actually unlocked, and you can unlock element that has complexity which are actually strictly greater than the element, either the first element of the array or any element that has been unlocked. What does that mean exactly? Let's say I have an array like this. If I have an array like this, that means this one is already unlocked, right? And since this one is already unlocked, now I can unlock this one using this one because this one is unlocked, so this one can be unlocked. I can unlock this one using either this one or this one because the two are actually smaller than this one, so this one can be unlocked. I can use this one or this one, but I cannot use this one to unlock this one. You got the idea? So you can use any element that is actually before an element to unlock it if the element you are using is already unlocked and has a complexity which is actually strictly less than the one you want to unlock. That is what we are saying here. And then now the question now is to find all the permutation of array where it can be possible to unlock all the elements in the array. What does that mean? For instance, if I'm taking this array, if I'm taking a permutation of this array starting with 4, this one will never be possible to be unlocked because let's say I have an array starting with 4, let's say 4, 2, 3, and maybe 4 here. This array will never be possible to unlock this one. Why? Because this one is actually unlocked. This one cannot be unlocked because this one is greater. This one cannot be unlocked since this one is greater. This one cannot be unlocked since this one is equal. So this array, this is a permutation. This is an array where we cannot unlock element. That being said, one thing we can see is that in order for this to be possible, the first element needs to be the smallest possible element in the array. Why is that? Because let's say I have 1 here, 2, and I have another 1 here. Since this one is unlocked, right? This one can be unlocked. This one cannot be unlocked because this one is equal to this one. So if you have an array where the first element is actually the unique smallest element in the array, then it is possible to have one solution. Let's start by that. Why? Because if this one is maybe a 4, then having the unique smallest element as the first element, we are 100% sure that all of the elements can be unlocked using this guy as it's already unlocked and is smaller than all of the elements. So that being said, we are getting out of this with one inside, which is the first element should be fixed and it should be the unique small element in the array. Now once we have that, the interesting part is that we can randomly put the other element, and by randomly put the other element, that means every single permutation of the subarray of n-1 is actually a valid solution type with the smallest element. That is the idea of solving this. Now that we have the idea, how are we going to solve this? To solve this, I'm first going to ignore this first condition and just return all the permutation of n-1, and after that I'm going to add the condition to make sure that it always starts with the unique smallest element, otherwise I return 0. So let us do that. For me to do that, I'm going to compute, to create a function here that is going to compute the number of permutation of n minus 1, which is actually called the factorial. So you can Google it and try to find out how it works. It's actually the factorial, number of permutation. All permutation of a subarray is called factorial. So how do we compute that? So factorial of n is actually a simple guy where just to give you, fact of n is actually equal to 1 times 2 times 3 times n minus 1 times n. This is how to compute the factorial of a number. So we can just use a recursion function to do this. So we have a condition here. If n is actually equal to 0 or n is actually equal to 1, what we do is that we return 1. And then else, what we will do here is that we return n times factorial of what? Of n minus 1. Now, since we just want to we know that this number can be really big, it has been said that you can return the modulo operator of based on this. So you can just put the modulo here, modulo 1, 2, 3, 4, 5, 6, 7, 8. You put this. And then, if you recall yesterday, we transform element into long to find ourselves out of what int can support. Another way of dealing with that is you can just put a 1 ln here. It's going to consider this as a long, so it will not exceed what int can support. So this actually helps us to compute the factorial, and here we can directly just return factorial of the complexity the size minus 1. This is actually the valid solution for each of the possible elements. What's this? Factorial of int. I didn't type this. Let us see what it will give. Okay, so it's working. So when we have something like this that has an output, it's actually working. We have solution. This is actually working. But those guys are not working because this should be 0. This should be 0. But we have this. So we should just now handle the 0 case. What is the 0 case we were just explaining? The 0 case is if we don't have a unique smallest element. That is the only situation where we should return 0. And how do we compute that? We just need to check. We just need to look for element from the first element. And one thing I was missing initially is the password for the computer with label 0 is decrypted and not the computer with the first position in the permutation. Initially, I thought that, okay, if I have an array like this, 2, 4, 1. Initially, I thought that, okay, this array can have a permutation which is 1, 2, 4. And then this is a valid solution. But what is encrypted is not the first element of the permutation, but the first element of the initial array. So in this array, for instance, the one that is unlocked is this guy. And if this one is unlocked, this one will never be possible to be unlocked because there is no element that will appear before him and less than him in a permutation. So this was the tricky part for me regarding this problem. So the guy unlocked is the first element. So how do we check it? We just check if I less than complexity dot size I plus plus. We just need to check if complexity of I is actually less or equal to complexity of 0, because the guy that is unlocked will return 0. That is it. If we have one element which is actually greater or equal to the first element which is unlocked, we return 0. And let us run again and see if it's actually cover the other test cases. Now we have everything working. Let us submit. Perfect, we have everything working. So this was my solution of this. I hope you do enjoy it. Feel free to give me any input. I'll be really happy to interact with you regarding this.